Hello student, to the Foundation of Classical Electrodynamics course. Under module 2, today we have lecture 40. So, in today's lecture we will going to discuss the boundary condition or the matching condition of the electric field when it goes from one boundary to one medium to another medium with separated by a boundary. Okay, so we have today class number 40, and our topic today is matching condition. Or boundary condition. So, before finding the matching condition, I should like to make a small note here, because we are going to use these things, and the note is this: the step function. Or in other words, we call it the Heaviside function. So, Heaviside function. So, what this function suggests? Let us define this function as h function, h for Heaviside, as a function of x, and this function is defined in this way: it should be equal to 1 when x is positive and 0 when x is negative. So, if I plot this function here, this is my axis, this is x positive, and along this direction I am plotting this Heaviside function h x. The plot will be like this. So, it is 0 here, there is a jump here, and it is 1 after that, and this is 1, this is 0. Okay. So, this is the form of the Heaviside function or the step function. Another important thing that one should note, that if I make a derivative of the Heaviside function with respect to say x, then I should get a delta function out of that. The derivative of the Heaviside function give me a delta function. Okay. Now, I consider a boundary like this. This is suppose a boundary. Okay. So, I am having a boundary like this, where some charge distributions are there. Suppose it is distributed over the entire surface, xy surface, and electric field is going from this direction to this direction like this. This is my z direction. Okay. So, this is the left hand side, I write it as L, and this is my right hand side, I write it R. For left hand side, the electric fields are represented like E L as a function of R, and the density, charge density, I write rho L as a function of R. This is electric field and this is a charge density. This is Z equal to 0 point. In the right hand side, similarly I have ER as a function of R and also rho R as a function of R. These are electric field and my charge density. So, let me write clearly what I try to mean here. So, here E L and rho L are the macroscopic electric field and charge density in the region L, that means the left side. In the similar way in the right side we have, and rho I already mentioned that rho is a surface charge density. So, rho x y is a surface charge density localized at Z equal to 0 point. Okay, this is surface charge density localized at Z equal to 0 point. Now, let us try to understand the electric field at every point in the space, how one can write it. So, the electric field at every point in space how can I write it? E R, this is the total electric field. Total electric field consists of the electric field in the left hand side, electric field in the right hand side. So, I simply write in terms of Heaviside function. I can write at electric field at right hand side, and then this is a function of R multiplied by the Heaviside function, which is a function of Z here. So, there will be no ER in the left hand side because I am multiplying with Heaviside function, plus EL, that is the left hand side function, and multiplied by the Heaviside function with minus Z. When I write minus Z, that means the Heaviside function will flip. Will flip means will have opposite. So, now I have negative sign 1 and then positive side 0. So, just put x equal to minus x here. I am doing the same thing. And what is the charge density? So, this is the total electric field, left hand side field, right hand side field, this is total electric field. What about the total charge density? The total charge density in a similar way, rho r is equal to, what is the left hand side rho? What is the right hand side rho? This is rho r with the Heaviside function like before. What is the left hand side? With the Heaviside function with minus Z, and whatever we have over the surface charge density, and that is at z equal to 0. So, I should use my delta function here. So, delta 0. So, that is the total charge density we are having. Left hand side this charge density, right hand side this charge density, and z equal to 0 we have a charge distribution here. So, that charge distribution I write in terms of delta function. Now, I have this equation in my hand, right, my fundamental equation, that divergence of E is rho by epsilon 0. That is the equation. I can exploit this equation according to my convenience. So, here we are having this. So, now E, total E I know. So, I will just simply write it. So, from equation 1, what I write, that total E I already evaluated. This is E at right hand side vector sign function of r with Heaviside function at z plus E L left hand side with Heaviside function minus of z, and that is all. But here you can see that this operator will going to operate both, because this is the Heaviside function is a function. So, this quantity is this. So, first I write Heaviside function as z, and then this is going to operate over E r. Then I have E r dot, then I have the divergence, the gradient of the Heaviside function with z, right, plus this is a straightforward vector rule I am using, plus Heaviside function, and then divergence of E left and plus E left dot gradient of Heaviside function with minus z. Okay. Now, this quantity I already mentioned that the derivative of the Heaviside function give us the delta function. Here Heaviside function is a function of z only. So, when we make this quantity divergence, so it eventually gives us the derivative, and that give us the delta function at z with the unit vector this. This quantity is also in the similar way give us delta function z, but in the opposite direction minus of z unit vector, because one negative sign I have. So, with that also I can have E dot r, that quantity, this one I can also have rho r divided by epsilon 0. This quantity I can write rho L divided by epsilon 0. So, all the 4 quantity I can write in this way. So, finally, what we get? We get divergence of E, that is in my left hand side, is equal to we are getting rho r divided by epsilon 0 multiplied by the Heaviside function, that is plus rho L divided by epsilon 0 multiplied by Heaviside function with negative z, these two, plus what I get? I get these two terms E r, E l and dot these things. So, I simply have z unit vector dot ER minus EL with the delta function this. Okay. Now, E dot E is right hand side, I still have rho by epsilon 0. So, this quantity is simply rho by epsilon 0, rho divided by epsilon 0. Okay. Now, I have also another equation. If I write equation, I am just exploiting equation 1, but equation 2 is suggesting that my rho is rho r, hz, rho l and sigma. So, I can write it here, is equal to 1 divided by epsilon 0 from equation 2, this red part I can write, and rho I write rho r with Heaviside function z plus rho L with Heaviside function minus z plus sigma delta function of z that I use. So, left hand side and right hand side, you can see that rho, this quantity will going to cancel out. So, this quantity will cancel out here, this quantity will cancel out here, and eventually what I get is this one, E dot r, E r minus E L dot z unit vector delta z is equal to sigma divided by epsilon 0 and delta z. Delta z again going to cancel out both the side, and I have my first matching condition, and that is E r minus E L dot z is equal to sigma divided by epsilon 0. So, these components are the parallel components. So, if I look carefully, that I have a boundary here, and whatever the E I am having, suppose this is my left side and this is my right side. So, here suppose I am on the right side, this is my electric field along R. So, and Z is along this direction. This is my Z direction. So and also EL is say along this direction is my EL. So, here what I am doing is that EL dot Z means ER dot Z means I am taking the Z component here along this direction, and I am also taking the Z component here, and this Z component I just subtract, and if I subtract and find that that value is equivalent to whatever the sigma I am having. Now, if sigma is 0, we can say that this component, this Z component of E and L are same. So, that means we have a matching condition. So, there is the Z component of E remain conserved in these two section L and R. In a similar way, we can do another, we can find another, because I have another equation. I just so far I exploit the divergence, I exploit this equation, but another equation is still in my hand, and that is the curl of E. So, now we have curl of E, this is also a fundamental equation, is equal to 0, right. If that is the case, then I can have curl of E, I know from equation 1, I can write it, and that is ER Z and then plus EL that quantity is 0. Okay. Now, again I can use this curl expression. So, here one important thing is that the right hand side is 0. So, I do not need to use the equation, I mean that one equation is sufficient, the first equation, this equation 1 is sufficient. So, I simply write here that this is nothing but ER cross the gradient of Z plus H Z, the curl of E R plus E L and then curl of minus Z, sorry, gradient of these things, and then H these things, and it should be curl of HZ and then curl of that thing, and then curl of EL. So, this quantity curl of ER, that will be 0 and that quantity is also 0. Since these are 0, so and so what I get is left with this quantity ER and cross Z unit vector delta Z minus EL cross Z unit vector delta Z, that is equal to 0. So, delta function I can cancel out. So, simply what I get is this, that is my another. So, ER minus EL cross Z is equal to 0. So, that is the parallel component. If I look carefully, so this is my second matching condition. The first matching condition is saying that E dot, so this is my first matching condition, is saying that E minus L dot Z is sigma divided by epsilon 0, and my second condition is saying that ER minus EL cross Z is equal to 0. When you make a cross, that means you are now talking the parallel component, because when you make a cross thing, so then it should be that it should be the cross will be perpendicular to the EL and Z both, that means it should be in xy plane. So, that is nothing but this parallel component, and this parallel component is always conserved. So, now after having this information, we can do few more things, and one of the thing is to find out the surface charge and the force on the conductor. So, the next thing we do is surface charge and force on a conductor. What is the meaning? So, we already for a conductor, so what we have, let me draw it. So, this is my E. So, this is my E out, say, and this is my E in. This is my E in. So, I already have this equation N cross E out minus E in is equal to 0. That is this equation, simply considering that is the z direction. So, now I am changing it, say this is my n direction and this is the boundary. And another equation is n dot E out minus E in is the I should put the vector sign here, is sigma over the surface for conductor over the surface I am having. So, R s, that is over the surface, this is R s, and this is epsilon 0, and sigma R s, as I mentioned, sigma R s is the surface charge density and n is the unit vector to the conductor of the this n is a unit vector along this direction perpendicular to the surface. So, now for conductor what happened, that E in, that is the inside the conductor, there should not be any field. So, E in should be 0, right. So, I am left with, if E in is 0, I am left with this equation n cross E out at over the surface is 0. So, the tangential component of the E out is 0 just outside the conducting surface. So, that means the tangential component of the field E out R is 0 just outside the conducting surface, just outside the surface. Okay. So, but another equation still I am having, that is n dot E out is how much? It is sigma, which is at R s divided by epsilon 0, as E in is 0, because E in is 0 here. So, whatever E in, that has to be 0 for conductor. If this is a conductor, then this is a conductor, then this inside the conductor we should have 0 field. So, from here we have a well known equation that just out what we are having? We are having the electric field as sigma R s divided by epsilon 0 in unit vector. So, that expression we already figure out in the last class. Again I am exploiting these boundary condition or boundary matching condition. So, this gives us sigma equal to, we can calculate it with the potential, because sigma here, and that is by simply calculating this quantity. So, this is the surface charge in terms of potential. This is surface charge in terms of potential. So, using the point is using the boundary condition that we discussed. This boundary condition is important, in many places we are going to use this boundary condition, where the tangential and perpendicular component of the electric field, how they are related, is given. So, using that we finally figure out that what is the field exactly the outside of the conductor, and that value is already we derived using the Gaussian surface. Last class I think we calculated that, and we are getting the same value. So, we are almost there, because today I do not have much time to discuss. In the next class we will continue that and try to understand that what should be the force on a conductor. So, I started here, if you look, that the surface charge and the force on the conductor, but this force thing I will do in the next class, and also try to do some problems. Suppose we have two conductor placed, hemisphere, two conductor, and how much force they exert on each other, that calculation we will try to understand quickly in the next class. So, thank you very much for your attention, and see you in the next class.